So students, now we need to understand about what basically is torque. Torque is the rotational analog of the force. But why do we need it? We need it because for any kind of rotational motion, we will find that the force is changing its direction, its trajectory is changing. So when the force is changing its direction, it is no more a constant thing. Therefore, we need something that should be constant, that will tell us about what is the direction, what is the net direction of motion. And for that, we need torque. And torque is based on the concept of cross product. So we'll apply the concept of torque or concept of cross product to derive the expression of torque. So let's see how do we derive it.
Now, as we mentioned, we'll now be moving on to the torque. So what basically does torque stand for? So when we talk about torque, torque is nothing but it's an analog of the force. When you have the force in linear motion, that has an analog in rotational motion given by torque, right? Like mass has moment of inertia, that we'll discuss later on, as the analog. Similarly, force has torque as the analog. So when we talk about torque, so torque is nothing but the net force that is applied to a body that gives the body an acceleration. Here, when we mean by acceleration, we are talking about an angular acceleration. Okay? So what we need to understand is that we need the force. So when we say that the force is required, it must be applied in such a way that it gives the body a twisting or turning action. So when it gives the body a twisting or turning action, that is what is meant by the torque. So in this case, what will we have? The torque will be given by the magnitude of the force into the lever arm. So torque will be equals to the force magnitude times the lever arm. So here, depending upon what exactly is the force. So this is the force that has been acting, and so this is the lever arm of the force, and the force has been acting along this. So this force perpendicular to the lever arm results into the motion of this object. What does that mean? That the quantitative measure tendency of a force to cause or change the rotational motion of a body is called torque. So torque, what does that mean? It is basically magnitude of the force that has been multiplied with the lever arm. There can be any angle between the force and the lever arm. Since this is a cross product, you can see that these two quantities are perpendicular to each other. So this is nothing but a cross product that we have. So torque is found by force times cross product with the lever arm, right? So to come back again, we'll say that the quantitative measure of the tendency of a force to cause or change the rotational motion of a body, that is what is called the torque. This body can rotate about an axis through O. So this can rotate about this particular point perpendicular to the plane. Obviously, when it is going to rotate, this and this both are causing the motion, and therefore they are going to rotate perpendicular to the plane. Therefore, we will say that it is acted by three forces. So they are going to be acted upon by three forces, F1, F2 and F3. So these are the three forces that are there. The tendency of any force to cause the rotation depends on the magnitude of it and on the perpendicular distance. So what will we have? So the tendency of any force, it can be F1, F2 or F3, whichever causes this object to move, that is because of the amount of the force that is acting on it multiplied by the magnitude of the distance, magnitude of the perpendicular distance acting at this particular point. Yeah. Now let's take this further and try to understand more about it. So let's assume that we are trying to rotate this. This is a nut, let's say. We are trying to use this syringe to rotate it. So in this case, there can be different amounts of forces. So let's say there is a force acting here if you try to move it using this, or if you try to move along this, and similarly you try to move at this particular point. So which one is going to cause you the most amount of force? Which one is going to require the most amount of force? Obviously, since in this case the distance is less, to move it by a certain amount, you need to apply the higher amount of force. In this case, the distance is along, so obviously this is not going to make the object move. The only resultant best case is the force FB, because it is at an optimum distance from this. Since this distance is less, so the force required here is going to be minimum. Fine. Going further, we can say that this torque is a vector quantity that measures the tendency of a force to rotate an object about an axis. So what does that mean? The magnitude of the torque is going to be defined in the same way like we define the cross product. So torque tau is going to be defined as F into L, where L is the momentum and force is the force exerted. So if you try to write down L in terms of the radius, so you can say that it can be written as R into F sine phi, or you can say this is nothing but F tangential into the radius R. So what does that mean? Here R is the distance between the pivot point and the point of application of the force. So you have written down L in terms of R basically. F is nothing but the magnitude of the force, phi is the angle between the force and the line extending through the pivot and the point of application. So it's basically the angle between R and F that is there. F tangential is basically the component of the force perpendicular to the line, or you can say it's a tangential force connecting the pivot and the point of application. And finally, the value of L that we have is nothing but R sine phi. R sine phi is equals to the momentum of the lever arm. So it's equals to the distance from the pivot to the line of action of the force. So this is what we have. Right? Let's go further. So when we talk about this, so we'll say that torque, if I have to find out what is the value of torque, if I have to visualize this, so how am I going to visualize? I'm trying to move something here. So obviously this object is going to move out of with respect to this particular point O. If I say that I am applying a force here along this direction, obviously this is not going to help the object moving. So if I try to find out the component, so one is going to be a radial component, one is going to be a perpendicular component. This is the radial and this is the tangential component that you have. The tangential component is going to be F sine phi, the radial component is going to be F cos phi. This is the line of action. So R acts here and the angle between R and F is equals to phi. So what you are going to do, you are going to write down L as equals to R sine phi. So this is the line of action. So along the line of action, if you want to find out, so that's going to be R sine phi. That gives you this. Therefore, what is going to be the torque? Torque will be equals to F into L. So F into L is going to be how much? F tan, that is the tangential force, into the radial vector. So it's going to be Fr sine phi. So this is what we are going to get. Is that clear? So torque is equals to Fr sine phi. So when I say torque is equals to Fr sine phi, so torque is going to be out of pitch. It's going to be perpendicular to this. So it's going to be coming out. Taking this further, we'll say that torque has units of Newton meter, the same units as the units of work. Mind you, work is a scalar quantity, torque is a vector quantity. Right? So engineers will often use the term moment and physicists will be using torque. We will adopt a convention that defines torques that tend to cause clockwise rotation as negative and torques that tend to cause counterclockwise action. So this is just a convention. You can use the opposite convention as well, but you have to stick to your convention. Further, torques are always defined relative to a point. If you do not find out the torque with regard to a particular point, you cannot really explicitly define what exactly is the value of torque. Right? Going further, we'll say that for a more general definition for the torque, so we'll say that it is a vector cross product when a force acting at a point which has a position vector, let's say R, related to origin. In that case, the torque is going to be defined as R cross F. So this is how we define torque. Going further with the directions, we can say that if you curl your fingers around this, so let's say you have this something like this, you curl it around this. So the direction of the curl, so let's say this is the force, this is the radial vector, and this is perpendicular to this, you are getting as the force. In that case, you curl your radial vector along the direction of force, then the perpendicular to that, that is along the direction of thumb, gives you the direction of R cross F, that's the torque. Or you can just try putting in the screw, or you tightening in of the screw. So depending upon which direction you are going, so when you are tightening the screw, it's going to go down. When it goes down, in that case you have the direction of torque going down, or it's going to go up. So depending upon where exactly, which direction you are moving, that will tell you about the direction of the torque. Fine. Now we have defined about the torque. Now we need to relate that to the angular acceleration, because we said the torque is an analogous quantity to the direction of force. Force in linear motion is analogous to that of torque in rotation motion. When we talk about this, so let's say this is the radial vector that we have. The force is acting along this. So we can break the force into these components. You can have one along this, you can have one along this, and this is the radial. So all these three components are perpendicular to each other. So this can help us in understanding that if we consider a rigid body that is rotating about a fixed axis, so this is a rigid body, let's say, and this is rotating about this axis of rotation. In that case, all the particles are going to satisfy the Newton's second law of motion. So we can basically from this we can show that the net torque that is acting on the body is going to be equals to the moment of inertia of the body about that axis times the angular acceleration. So it's in the way similar to the case of linear motion, because moment of inertia acts in the same way like mass does in linear motion. So torque acts in the same way like force does in linear motion, and instead of your linear acceleration we have angular acceleration here, right? Hopefully that makes sense. Going further, we say that just by default we'll take z-axis as the axis of rotation. Okay, now using this I have just tried to find out that if you have individual components, so let's say you have some mass m1 out here that is moving with an acceleration a1, so this is a force that is acting. Now acceleration can be written in terms of angular acceleration. Angular acceleration will be along the z-axis, so r1 into alpha z. So if I take that, so the net force, what will I get? The net force or net torque I should be saying, that comes out to be m1 r1 square alpha. But m1 r1 square is nothing but the moment of inertia of this mass about this particular axis. So this gives me the torque of this particular mass about the z-axis as I1 into alpha. So if you sum up over all the masses, whatever masses are given, so effectively you will be summing up mass into the radial square, because every mass is kept at a unique point. So m1 r1 square, that if you multiply it with the angular acceleration, gives you what is the net torque. So the net torque is equals to the net moment of inertia into the angular acceleration. Yeah, so that tells us about the basic of torque. So what does actually torque stand for? So this is what is the introduction of torque. Now the next topic will introduce further about what are the rotational laws that hold good when the object is moving in a circular path.
As we saw, to define torque, we need the force and the radial direction, because the torque is perpendicular to both the radial direction as well as the force. The force should be acting along a tangential direction. When a particle is moving in a circular path, as we saw, there are two forces that are acting. One is the centripetal force, other is the force that is acting in a tangential direction. The force that is acting towards the center, that is the centripetal force, is not going to make the object move in a circular path. Therefore, we need to have a resultant force which we will get by the combination of both the radial force and the tangential force. From that force, we can find out what exactly is the torque. Now, since we have found out the torque, we need to go further and try to define the acceleration in the case of rotational motion. That is our next topic about angular acceleration. Stay tuned.